decay results in emission of either alpha particle, which are the spot on the right side, either beta particle, which are the spot on the left side, or the gamma ray, which are on the straight line, right? And after completing this experiment, they have made the conclusion that how the alpha particle or beta particle or gamma particle are made up of which element. For alpha decay, we can say that alpha particle is identical to that of a helium nucleus. They are attracted by the strong magnetic field. So the alpha particle, it means the helium nucleus. Now helium nucleus contains 2 protons as well as 2 neutrons. It is in this way. It contains 2 protons and 2 neutrons. By the chemical formula, you can write in this way. Here in the left side, ZXA is the parent nuclei. Whenever the alpha decay will occur, it will give us the daughter nuclei Y, which has the atomic number reduced by that parent nuclei 2. So the daughter nuclei has the atomic number Z minus 2, whereas the mass number is reduced by 4. It is the A minus 4, because one helium nucleus is splitted from the parent nuclei. So there will be the reduction of 2 atomic number and 2 mass number, because it contains 2 protons and 2 neutrons. Now this ZXA is the unstable atom. As we have discussed that the radioisotopes are the unstable, and to get the stability, they will emit the radioactive elements in the form of alpha, beta or gamma decay. So to get the stability, it emits the alpha ray in form of 2He4, and it will give us the Y daughter nuclei, which has Z minus 2 atomic number and A minus 4 mass number. So here Y is the more stable atom, and helium nucleus is called the alpha particle. Okay. We can see this alpha decay by taking one radionuclide example. Suppose we have radium atom. Radium contains 88 Z. It means the 88 protons, and total number of protons and neutrons are 226. Now when the alpha decay will occur, the radium nuclide, which is the parent nuclei, will disintegrate, and it will give us radon, which is the daughter nuclei, and it has atomic number 86, and its mass number is 222, and 1 helium nucleus. Now by this equation, by this figure, we can write the chemical structure of radium and radon in this way. We know that whenever the alpha decay will occur, the daughter nuclei will reduce the atomic number by 2. So here we can write this equation in this way. Now I am giving you one example. Suppose you have a radon which has a atomic number 86, 222 is the mass number. Now when its alpha decay will occur, you will get chemical element Y. Now identify this chemical element. What should be the name of this chemical element? Okay. You know that whenever the alpha decay will occur, your Z will reduce by 2. So your element Y has Z is equal to 84 and A is reduced by 4. So your A is equal to 222 minus 4. So now identify this element which has Z is equal to 84 and A is equal to 218. The name of this element is polonium. So when the alpha decay will occur, the radon is the parent nuclei will decay, and it will give us a daughter nuclei which is called the polonium. Okay. Now we will discuss about the beta decay. Friends, beta decay is nothing but the fast moving electrons which are coming from the nucleus whenever the radioactive phenomena occur in the nucleus. Whenever the neutron is converted into the proton, at that time the beta decay will occur. See here. Beta decay occurs when the neutron changes into a proton, right? It will emit 1 electrons. As a result of beta decay, the nucleus has 1 less neutron but 1 extra proton. Now, during the beta decay, you will get 1 more proton, but the mass number A will remain the same. Only Z will increase. Now when the Z will increase, it means neutron will decrease, but A is equal to number of protons plus number of neutrons, it will remain the same. See the example of beta decay. Suppose you have a polonium atom which has 84 atomic number, Z is equal to 84. When the beta decay will occur, it will give us the atomium 80, which has the 85 atomic number, and 218 is the mass number. So you can see because of the beta decay, there is a change in atomic number of parent nuclei and daughter nuclei, but the mass number 218 capital A, it still remains same. The chemical formula of the beta decay you can write in this way, that Z, when the beta decay will occur, the daughter nuclei will gain one more proton, and that's why its atomic number is going to change by Z to tends to the Z plus 1. By this formula you can write this equation. Now I am giving you a small exercise of beta decay. Write down or identify this chemical element X. You have a daughter nuclei lead Pb which has atomic number 82. Now we know that whenever the beta decay will occur, there is an increase of atomic number in daughter nuclei. For this reason, the parent nuclei X should have atomic number 81. Now name the name of the Z is equal to 81. What is that element? It is a Tl thallium. So in this way you can write the equation or equation of alpha decay and beta decay. One more example of bismuth. Suppose after beta decay your daughter nuclei is bismuth which has atomic number 83, and the beta is the electron, right? So identify the chemical element X. It is nothing but the lead Pb which has atomic number 82. Now the gamma decay. Friends, gamma rays are not the charged particles, right, like alpha and beta particles. Gamma rays are the electromagnetic waves. It has not any kind of charge. But one thing is interesting is that gamma rays have much more energy compared to alpha and the beta rays. That's why it has the more penetration power compared to alpha and the beta rays. You can see when the atoms decay by the emitting alpha or the beta particles to form a new atom, still they don't get the completely stability. Still there is some energy in alpha decay or alpha and the beta decay in the new form atom. Now to get this stability, they have to emit that energy in the form of gamma rays. So when the alpha or beta decay will occur, the nuclei of the new atom form may still have too much energy to completely stable. For that reason, the gamma rays will occur, which has the energy of 1 into 10 to minus 12 joule. Note that. Please keep in your mind that radiation is nothing but the energy in transit in the form of high-speed particles and electromagnetic waves. Now there are two kinds of radiation. One is the ionizing radiation and the second is called the non-ionizing radiation. Now what is the difference of ionizing radiation and the non-ionizing radiation? Ionizing radiation, it means the radiation by which the electrons can emit from the bound atom. By this radiation you can emit the electrons, means electrons can be dispatched from the atoms or molecules. It means that radiation has sufficient energy so which it can emit the electrons. But the non-radiative elements, non-radiative transition, it means the radiation has not that much energy to eject out any electron from the atoms or molecules. The example of ionizing radiation is the gamma rays, neutron rays and X-rays, which has a sufficient energy to eject the electron from atoms or molecules. But the visible rays, like the light rays, that have not that much energy to eject the electron from any atoms and molecules. You can conclude this by using the concept of Einstein relation E is equal to hc over lambda. You know that the wavelength of X-rays or gamma rays is around few angstrom. So by E is equal to hc over lambda, when you put that values of lambda 1 or 2 angstrom, you will get that energy which is sufficient to eject an electron from the atoms or molecules. but the wavelength of the light rays are around 4000 to 7000 angstrom. When you put this value in E equal to hc over lambda, it does not the sufficient energy to eject electrons from any atoms and molecules, because atoms and molecules have also some ionization energy which is around few electron volts. This was the concept of ionization radiation and the non-ionization radiation. Now, after completing this, we want to discuss about the half-life time. Friends, what is the meaning of half-life time? Half-life is the time it takes for half the atoms of a radioactive substance to decay. It means it is the time by which the half of the radioactive substance will form another atom, another molecule. In this time, suppose you have 100% atoms or molecules, then 50% atoms and molecules will convert into another atoms or molecules in a particular half-life time. Now, every atom and molecule, means the radioactive atom or molecules, have a different half-life time. We will understand it better by taking one or two examples. Let us see. Suppose you have 5000 atoms of a radioactive substance which has a half-life of 1 hour. How many atoms of that substance would be left after? How many substance will be left after in 1 hour? You can calculate it for each and every 1 hour. According to the definition, if you have one half-life hour, so after 1 hour there should be 2500 atoms should be the radioactive nuclide, and another 2500 atoms or molecules should be the other atoms, right? So 50% are the remaining. After one more half hour, it means after 2 hours, you can see in the table the 1250 atoms will be the radionuclide, 25% only the remaining form. After 3 half-life time, the 625 atoms or molecules are the radionuclide. So in this way, by the half-life time, the half of the atoms will decay and it will give us the new atom or new molecules. Okay. So by the concept of half-life time, you can measure the material's age. This was the benefit of the radioactivity phenomena. By picture you can see here is a radioisotope material, whatever your radioisotopes which has atomic number greater than 84. At start, suppose there are 16 radioisotopes. After a 1 half-life time, what will happen? After 1 half-life time, the 8 atoms will form the new atom. You can see in the picture the new atom form, and the 8 atoms remain as a radionuclide. After one more half-life time, the 4 atoms will be now the radionuclide and the 12 atoms will in the new atom form, right? After one more half-life time, only 2 atoms will be in the radionuclide form and the others are 14 atoms are the new atom form. This was the process of the radioactivity. And by this phenomena, you can also draw a graph of count versus time in this way. After 1 half-life time, the 50% of atoms will form the new atom. That's why it is the 50% in the radionuclide form and 50% in the new atom form. I can give you 2 exercises. Here are the 2 examples. In first example, what is it? You have 400 milligram of a radioisotope with a half-life of 5 minutes. How much will be left after 30 minutes? Calculate it. You have a half-life of 5 minutes. Initially, you have 400 milligram of a radioisotopes. So how to calculate the number of atoms after 30 minutes? Now, according to the half-life time definition, after each and every 5 minutes, the atoms will decay and it will give us the half of the atoms which are the radionuclide. So here you can see after a 5 minutes that 400 atoms would be the 200 atoms. Then each and every 5 minute interval it will decay, and at the last 30 minutes what should be the number of atoms? After the first 5 minutes the number should be 400 to decay to the 200. Then after 10 minutes that 200 will give us the 100 radionuclide. After 15 minutes 100 will give us the 50. After 20 minutes, that 50 will give us a 25. And in this way, at the last, you will get the 6.25 milligram only atoms which are in the radionuclide form. Here is the answer. Similarly, for the second calculation, suppose you have 100 milligram sample of Au gold, 191 is the atomic number, which has a half-life of 3.4 hours. It means after 3.4 hours, the half of the Au will convert into the another new atom. So what should be the atoms after a 10.2 hours? Friends, suppose initially it's a 100 milligram sample. After one half-life time, 100 will give us the 50 milligram of the Au. After the second half-life, the 50 will give us the 25. And after 3.4, 3.4 plus 3.4 plus 3.4 will give us the 10.2 hours. So after the 10.2 hours, there should be the 12.5 milligram substance in the Au form. This was the calculation of the half-life calculations. Now suppose anybody can ask you what should be the number of atoms except the half-life time. How to calculate the number of atoms in the radionuclides in any time? For this thing, we have a formula. See here, a radioactive sample contains if n0 number of radioactive atoms, and if after a time t you have only the number of radioactive atoms are n, then what should be the formula for the radioactive? For that things, the n is equal to n0 into e raised to minus lambda into t, where lambda is a decay constant. Now if you know about the half-life time of any radioactive nuclide, and if you put here t is equal to that half-life time t, and you can put n is equal to n0 by 2, because at the half-life time the half of the atoms will decay. So by putting that values, you can calculate the lambda, which is called the disintegration constant. Using this formula, you can calculate the number of atoms at any time, and by this formula you can also know the age of the any material. What should be the age? So in this way, the radioactivity phenomena is very helpful to us. Now what is the unit of radioactivity? The SI unit of radioactivity is becquerel, which is equal to 1 disintegrations per second. But it is a small unit. The bigger unit is the Rutherford, which is equal to 10⁶ disintegrations per second. And still bigger unit is the 1 Curie, which is equal to 3.7 into 10⁷ disintegrations per